to this day I still don't understand. And I just reviewed it and it's a proposal that didn't even show that, and they were going to do all production using breast height diameter, which also drives me insane. But we have many other ways of doing it, but you've got to do what you got to do, and it all is related to production. So basically, Rudolph Jaffe would give this talk normally, and he's our organic geochemist. So he'd be looking at the specific compounds that are coming through the system to understand where the mixing is, where they're coming from, and where they're going. I'm the isotope person, so I try to apply the isotope approaches to help this out a little bit more and tease out these differences. So he's going to be using optical properties and fluorescence. Is everybody familiar with this approach? I'm not. We did it on the ship. So looking at different wavelengths of the light that's coming off of the organic molecules tells you different properties of it. So I'd be lying to you if I told you what that is. And then obviously the composition of a particular organic matter, which we use biomarkers from. But one of the big things, and is there a way to move this, or is that just, we're stuck?
It's just stuck.
All right. So this is 0, by the way. That number would be 0. Because remember, everyone's got to talk about their axes when they talk to you. This is concentration of dissolved organic matter. Dissolved organic matter is a big deal in the Everglades because it's going to be a nutrient source, and it's moving carbon. So if we think about SRS6 going from a fresher end member down to the saline end member, you can see in general, as you're increasing salinity going out, you're getting decreased salinity. Sorry, decreased DOC. So if you've ever done this, and I know you've done this many times, who's done this? So what's the first thing you notice when you start moving from here to here?
Vegetation change.
Vegetation change. If I took you out to here, what would be the biggest change from here to here?
Mangroves are bigger.
Mangroves are bigger. Further out here, I'm thinking even something more basic.
Salinity.
Salinity. What else?
Nutrients.
Yeah. Thank you. Absolutely. So DOC, we actually have really good water quality here, but higher DOC. Because you're getting all this stuff coming from the freshwater end member, mixing with the saltwater end member. That DOC is organic carbon flux coming out of the system, right? So in general, you see the trend. So basically, this is SRS4, SRS5, SRS6, the deltas, the pluses, and the circles. But these are measured at different times of the year from the LTR database. So you do have salinity changes, but in general, you see the decreasing trend as you go to C. This, the upper graph here, is part of a tracer study that was done with SF6 at the University of Hawaii. Anyone familiar with the SF6 approach? Have you ever done it?
Yeah.
So people use SF6, and we had a mass spectrometer here that was actually made to measure it. The old prism, which no one ever saw, which we gave to U of F because it failed after many hurricanes. We were to get it back on. Has a very special flight tube made to measure SF6. SF6 is a non-naturally occurring compound. It's conservative. You put it into the water and you trace it as it moves through a system. And originally this was supposed to be done Lagrangian approach,
Yeah.
whereas you put a tracer in and you measure the water as it goes through, instead of just being at fixed points with fixed sampling stations. So David Ho's group put it up at 1, and we tried to trace that water as it moves through the system down, so that way we can know exactly where we're at and where that water is. And if you remember from the original hypothesis from the FCE, which I didn't show, do you know that slide?
I do.
So you have this mixing between the salt and fresh water. This idea is there's expected to be a productivity hump in the middle, but depending if you're in Shark or Taylor, it's not necessarily that way. You actually see gradients. But we actually see a bit of a bump in this data. Up here we have the delta C13 of the organic matter going through the system. This is basically delta C13 of this is DIC. This is amount of DOC here. And this is DOC and DIC, showing a comparison of the isotope value. When you get to carbon isotope values about -1, that's like normal marine. If we go towards 11, the Everglades can go all the way to -15, that's freshwater end member, typically, because of recycled carbon. Take my class, we'll go over it more. But it's a very nice tool to see where we might be having some respiration. This line is not necessarily the conservative mixing line, because that's a ratio, but they did put that line in there to show you that. And this is the DOC going through the salinity, going towards open marine to the freshwater end member. And we do see there is a relationship, but there is a bit of an arc here. So
What's
on
that,
this
is the
side,
y-axis there that's covered up?
that's DOC, that's concentration.
Okay.
And this is, and by the way, they reversed my axes, and I hate that when people do that. Sorry, but they flipped it, not me. This is mine originally. It's not flipped, but that's how I roll. Anyways, it's an interesting end member, and we know we're going marine versus the mangrove ecotone here with the sampling. So these are samplings taken through this study, trying to basically, on different days, measuring this pulse, if you will, the center, the back, and the front of it. During the entire study in 2010 and 2011, there was constant transects done going from saline to freshwater to look at these differences. This is from Rudolph students that use the Google Earth to put those in. And this is basically looking at Tarpon Bay, the Harney River, and the Shark River for DOC concentration versus salinity, and one of their fluorescence. This is one of their, this is what they're calling colored DOM. So you could select different wavelengths you want to analyze for. This is the one they selected. I'd be lying to you if I said why. But what you see is, if you look from 0 to 40, well, actually something's only going about 28, 29. You see that wherever you are, you don't have a conservative mixing line. Salinity is great for looking at mixing between end members, freshwater versus salt, because it's very conservative. But if that colored DOM contribution was just from mixing of two end members, you wouldn't expect to have this extra coming in right here, which is actually exactly at the ecotone. So the idea is that if you considered, then they break up into fluorescence. They know what the mangrove source should look like, and then they know what basically the periphyton source would look like, which is very conservative, by the way. And what they've identified, so they take mangrove-derived DOM, they know what it should be, and then when they look at their samples, they focus on that, and they see that right at the ecotone, obviously you see non-conservative behavior, you see an increase in those compounds where the ecotone should be. So we know we're adding carbon at that point, kind of with the original FCE hypothesis. We also can use these things to trace, basically we can use the word fossils, but they're like geochemical fingerprints of the biomass, where it's going and what it was. And that's how we know we're looking at freshwater versus mangrove inputs. But there's many other parts of it you could look at. You could look at just not like the transects we're looking at, but also look at tidal effects and seasonality. So the idea is that you know by if Shark River, you look at water clarity, the water is pretty good. It's not suspended solids, it's a dissolved organic carbon in that system that's affecting it. You have mangrove inputs, you have the freshwater organic matter coming from the headwaters to the north. You do have primary production. We have evidence that maybe some of the values we see are coming from also algae associated with the mangrove roots themselves. You can have resuspension events too here of the organic matter in the system. So when they look at things from an organic geochemical point of view, they typically have a 3-end member mixing model between periphyton, diatoms, and mangroves. Traxol, I remember, because that was when I first arrived here. They were isolating that compound from cores in Florida Bay. So looking at Traxol abundance through time to see how mangrove-derived organic matter affected different parts of Florida Bay. The periphyton, these are highly branched isoprenoids. Am I saying that right? Organic people help me. Versus the C25, which is associated with marine diatoms. So this is really one of the biggest strengths of the organic matter working group, is that Rudolph Jaffe's group is really, he's a very well-respected organic geochemist. So they can actually use these different carbons to identify things very specifically. So sources. So going from SRS-1 to SRS-6 to offshore, to GOM, Gulf of Mexico, the abundance of the freshwater biomarker follows this suit. This is relative abundance on this axis. Versus the marine end member down there. And then the estuarine member in between. So this is the work of this PhD student who's now as a postdoc at Georgia Tech. So they use these different mixing models to understand the suspended particles in this part of the world. And this is a nice system to work in. As I said, you have end members. It's not always clean, but you have high tide versus low tide, and this is basically their conceptual model of how they see things, where the organic matter is coming from. Whether it's freshwater derived, whether it's from the ecotones, mango derived versus completely marine part of it, which usually focus on seagrass because it's so unique isotonically. So why do this work? Because if you understand what the carbon is, you got to understand where it's going. Is it staying around? And think of it like this. We know the carbon here. How do we know the carbon stays in the Everglades system? The greater Everglades system. I don't care where you go. How would you prove to someone the Everglades has value because it has carbon? Are we fixing carbon or losing carbon in the Everglades system? Fixing. Fixing. Is it staying around? But how do you prove that to someone?
We have land that grows.
Peat soils.
Thank you. Exactly. We do. You have carbon accumulation, but marls are carbon too. So we know it's staying. We're accumulating peats. We actively show this. We have the set stations out there showing sediments. You got some people would say soils. I would say sediments. It's all okay. But the point is, it's there. Now, it does undergo differential rates of oxidation depending on what's going on. There are many other processes that occur that deal with sulfate-methane transition, which we would like to study a little bit more. And I gave a talk on that when we talked about the ship stuff. But all that stuff can be applied to the here, and I hope to do that. So the idea is, where do you have carbon staying around? Where do you have carbon loss? The tower data shows stuff is leaving. So you have to quantify that. So during this study, we do go out. They take tons of samples just to understand where the marker is. This is basically looking at the SF6. This is a mount of SF6 in the tracer on day 1. And they're going up all the way down the river, taking samples across salinity to try to figure out where the tracer is exactly. On day 2, the tracer is more diffuse. And this is when we start sampling. This is for a tracer study that happens over about 5 days total. We sample at the back, the top, and the front. And we go through and take 3 samples, actually more than 3, each day. And this represents day 1, day 2, day 3, day 4, day 5. And this is just concentration of DOC through the study, taking all the data and plotting it for you. Also remember, when you're in the field, you're limited by time and money. I hate to say it, it always comes down to money. What's nice about what Rudolph's group
Someone just came in and turned off the TV. Did you see that?
I'm on Mike's committee. Why
Who
do
was
you
that? He just left it. Someone else came in.
He texted me earlier and said that he's going to have to leave after 15 minutes, but I don't think he realizes.
What do I do to go back to what I
Yeah.
want to see?
No, somebody else came in,
And did
picked
that-
up the remote, and then
Turns
turned
it
it
off,
off.
some like mystery person.
Yeah.
The story?
I mean, I guess there's nobody in there, so don't worry about it, right?
They can call us, I guess.
Yeah, just to be able to get back to our presentation.
There it is.
We get rid of the other part.
It'll
Either
go
way,
away in a minute.
What's nice to see is that this is isotopes of total organic carbon. If you filter, it becomes dissolved organic carbon, and this is the DIC. This is something we do for FCE, and Tiffany has started a lot of this work too. This idea is that when you look at carbon export, you just shouldn't focus on the dissolved organic carbon. You also have to consider the dissolved inorganic carbon. And what is the definition of DIC? Dissolved organic carbon. Well, what is it? You know, you're professional. What does CO2 dissolved water really mean? It's a fundamental thing. I see it asked in a lot of masters and PhDs.
Carbonate,
Carbonates.
equilibrium.
My oceanography class just had to answer this.
Carbonates and bicarbonates.
Yep,
And carbonic acid.
yep. So do you store more water, more CO2 in the atmosphere or water? At the end of the day, who's doing most of the work? Water. Multiple forms. But pH. So most, at the pHs we have here, most of it should be bicarbonate, HCO3. People forget that. They always think DIC CO2. No. Very small amount of CO2 is actually dissolved. But what's interesting to see is going from the freshwater end member to the saline end member, you see DIC going down right in the ecotone. Isotopically, this is an isotopic value. Going back up to open ocean. That's exactly where that mixing's happening. That bump is really there. Just here it's a dip. It's quite cool.
So, I'm sorry if I missed this, but why is it going down exactly?
It's going down because it's mixing and you're probably getting oxidation of the mangrove organic matter contributing to the inorganic parts. When that organic matter becomes oxidized, it is relatively negative. The organic matter from mangrove isotopically is about negative 27-ish, plus or minus 2, depending on what's happening to the planet at that particular time. So what's interesting to see is you even see the contribution of that negative material to the inorganic side of it. It's quite cool. The next step is to get the fluxes down and do it. The only problem with the Lagrangian point of view is that they still haven't given you the flux from a certain point in time. You can calculate it all. It's all available. And there's a big effort and paper that's actually in draft form coming out about the fluxes. It's a little dirtier in the TOC data, but the next year the data shows a little bit better. But if you notice, the values are very, very negative. This is, by the way, a brand new isotopic approach. So the DOC is coming down almost negative 34. It's really, really negative, and I didn't really have a great way to explain that. I'd be lying to you. It's the outer limits of what I would expect a terrestrial plant that's emergent to be. And I didn't realize we measured what it could be when I first came here, and I totally forgot. And Jim Fortner was the one that reminded me of the values we had measured previously with one of his master's students in Southwest Florida. The algae associated with mangrove roots can be negative 40. There's very low light penetration, but it's very extremely low production, so that there's no isotopic. The isotopic fractionation is almost diminished. So you're fractionating at the maximum ability a plant could do. Sorry, when I say plant, primary producer, forgive me. And you get these crazy negative values. So you have contributions from other organic matter and just not mangrove. And sorry, this is year 2, and you see a similar bump. This is salinity. This is delta C13 for DOC here, because we have no budget, we only measure it once, and then DIC. And you see exactly the same thing, again coming down here and going back up. This is the seagrass field. This is sawgrass mangrove field. But the point is, the biomarkers, other method approach, fluorescence, isotopes help you really get at what you're looking at. Another straightforward point of view, and it goes exactly back to what you said, we know we're keeping carbon around because we have peats. I mean, it's not rocket science, right? Peat is organic matter. This is the work of Donnie Smock's group, and this goes back to one of the original reasons why we're working in shark peripheral and the extra work with regard to FCE, because we have the eddy covariance tower, we have NPP, and the idea is how much carbon's leaving the system. That's where we come in. This is some of Donnie's work looking at basically, I'm going to be showing you data right from here. The tower's at SRS 6. There is some debate about the tower's placement because it is an island. It has some other unique effects. But just to show you what's going on, he took many cores from this area to try to show you what the rate of organic matter accumulation is. So basically, Donnie Smock's a really nice guy from USF. He's in basically like the environmental sciences department there in St. Pete. He is a short-lived radioisotope person. This is a wonderful technique for dating cores, dating resuspension. I've worked with Donnie and Reed Corbett at East Carolina. But basically, to measure soils or sediments, as I would say, the short-lived isotopes help us date things we can't date with radiocarbon. So if I want to take a meter core and tell you how old the peats are, lead-210 is one of the best approaches you can use. Cesium is another approach from air explosions of atomic devices, but usually it's very mobile in peat, you have to be careful using it. So basically, they slice the core up, take a 1 meter core, slice it, those discrete intervals are then put in their gamma ray detectors, and they make their measurements. The basic depth through time.
We have about 5 minutes, Bill, if that's
Okay,
okay.
I want to wrap it up. Oh, crap. That didn't translate for SHIT. Okay, long story short, last time I gave a talk in Europe, I actually said what you would have saw, and they made fun of me. What you would have seen would have been the accumulation rates, and shockingly, yes, accumulation rates are going up through time of organic matter, so we know it's working out, but I would have gave you specific rates. And what you should have seen here, too, is that he has taken 1, 2, 3, 4, 5, 6, 7 cores across the area, showing this is basically organic carbon accumulation rate, organic matter accumulation, organic carbon accumulation rate. And the different symbols are 110-year average, 50-year average, and 100-year average. When you spread out the average, it just brings it back through time. But basically, we're increasing the amount of carbon we're accumulating presently.
Why is that? Is that the...
I don't have a perfect answer for that. I'd be lying to you. It could be everything from increases in CO2 to water levels in that region. I don't know. But the point is, if you're going to look at carbon export, then we have to know how much is staying. And now we have that, and which you can really wonderfully see. We also, and I lost all the axes here, so obviously it doesn't translate. We have a very nice system at Rasmus, and this is looking at different metals. We actually look at dust deposition through time in this. We know that dust is going to be an important component for productivity. And just to wrap it up quickly, the end member of Florida Bay, this is a publication that just got accepted. The first time we used the new CRDS system to actually quantify the isotopic composition of the DOC in Florida Bay. So remember, everything that's happening in Shark, as it comes around, and Taylor, that end member is Florida Bay, and that is going to get there. So basically, these are different sampling stations throughout Florida Bay, and this table just basically tells you if you're northeast Florida Bay, you have this wide, slendy variation depending on seasonality, where's the wet or dry season. And we'll cut to the chase, which really, and you can't see this because of this. What's really cool about this is we now have proof to show you how much influence the freshwater end member DOC has on Florida Bay, coming from Taylor, and actually contribution to the mangrove islands themselves. This is really wet season. This is isotopic composition of dissolved organic matter. If you're going towards -10 and greater than that, that's a seagrass end member. -22, it's heavily mixed, but the biggest component is mangrove. Coming into the late wet season, this is also a lesson. The magnitudes change, and I forgot the PhD student didn't change the colors with the magnitudes, so keep in mind the absolute numbers are really changing. During the late wet season, we see a much, much higher contribution of mangrove-derived DOC coming down. That's not shocking, by the way, but at least now I have a straightforward method to show you when that's coming down, because you would expect it, higher water flow. If you work here in trout, it's freaking all mangrove, you know what I mean? It's all mangrove. But it's nice that we actually show you quantitatively how much is coming down. And then the dry season, it flips the other way, and the mangrove contribution goes way, way down. So it's a nice way to show that effect. And then she did a nice job of modeling. This is a table showing seasonality, the central versus eastern versus western Florida Bay, showing the proportion of seagrass within that system. So, long story short, we have ways of looking at the organic matter. We're presently understanding the accumulation rate. We know we have loss. We cannot ignore the inorganic forms, but we have to do a better job at collecting that data. Tiffany Gantroxer has a lot of that data. We will have some of it too. So that's coming together. And I think moving forward, when you're integrating these carbon budgets, you have to think about everything. So sorry I lost all the freaking answers. But Donnie Smock's work is really nice, and Xiao Yao's Gal's data is also coming out at Continental Shelf Research right now as we speak. So we're moving forward with these techniques. And there's many more people working on this too. I only scratched the surface. But I hope you see the general trends. Higher DOC in freshwater, lower in the seawater end member, but there's a seasonal component to it. So if you understand the whole carbon budget, you can't isolate one transect or one season. I'll shut up. Thank you. I hope I was a little bit coherent.
Great, thanks.
We have time for 1 or 2 questions if anybody has a question.
Did I say anything wrong?
No, I thought it was straightforward, yeah.
So the tracers, it seems like for the freshwater, you're mostly using periphyton. Is there a reason not to use sawgrass or any of the other macrophytes?
I'm not sure, because when I look at the older peats from Florida Bay, those peats, which everyone calls mangrove peats, isotopically they match sawgrass. But that also makes sense, because we think of this classic model where when sea level is lower, Florida Bay is in essence the rest of Florida, right? It is the Everglades. When sea level comes back up and covers it up, you have that transgression in the mangroves, but you know certainly the diatom data from the basal peats show that there are diatoms associated with sawgrass too. In this application, they chose to go that way. I also think it because it is a very unique biomarker. When they first saw it, they thought it was contamination of petroleum. But where we're working, it's trout. I don't know if you've been to that southern Taylor Slough area. It's Trout Cove. You know what I mean? People are going there fishing. I'm sure they're not dumping fuel, but it turned out that it is related to diatoms. That's why they chose it. Yeah.
So if we wanted to essentially look at some integrative work from a different group, like from the trophic dynamics group, to working with some of the carbon people, how would we get around? How would we do that? What would be the easiest?
Well,
mechanism?
I always make the argument carbon's a common currency, but not everyone agrees with me. Obviously, I wasn't in round 2, but I think that's the way to do it. But I think it gets harder for the upper trophic level because it's a sampling thing. You know what I mean? But you have it. You know the mass of the fish. You know you have your gates. You know what's going up and down. You know what I mean?
Yeah. But is there even a meeting that we could stop by and present something?
Well, I
See if it
think,
makes any sense.
I hope, look, this ASM is going to be the review, right? Preparation for the review. So I think it's a time to do that. But the ASM was never really ran in a way, and this is not for fault, but it wouldn't have been nice for working groups to get together and then have cross meetings. We've always been so focused on the proposal and the process, and that's where you get that. But it also takes, maybe the student group should say that. We would like to propose at the next ASM a cross-cutting theme of, carbon across trophic levels.
One thing to keep in mind is that the working group leads that are presenting at the ASM and the review are going to meet in December, and the point is to have these kinds of talks visualized among us, and maybe the student group can be involved in that in some way to kind of stimulate those.
Wouldn't that be cool if they did
ideas.
like an integrative talk? You know what I mean? That'd be
Yeah.
kind of really cool.
And maybe we could, try to get something post-review as a follow-up.
But I think that'd be really important, because that's every ASM, every LTR, every review. If you don't put the pieces together, that's the most critical part. Anything else? Anyways, we also, just so you know, there are lots of analytical facilities that can help everyone. Make sure you take advantage of them. Tons of them. And the R Lab is always happy to work with you. That's it?
Yes.
All right.
Thank you.
Yeah, thanks, Bill.
We got first.
All right, I gotta go to lab meeting.
All right.
See you guys.
You won't give you the paddling stuff.
Yeah, if our lab meeting runs late, what time are you leaving today?
I don't know, like
Oh, 6?
something like that.
Cool, yeah, I'll try stopping by. Are you be around tomorrow?
Yeah.
Cool, if not tonight, I'll catch you tomorrow. Cool, man.
Oh, I sign your release.
He sent me an email saying to
You
sign,
guys,
and
the
I
kayak
digitally
one?
sign
You're
it,
buying a
and
kayak,
send it back.
right?
Yeah, we were blocking.
Thank
That's just what I
you.
have.
I apologize. But I have to write
That's
someone.
okay. No, I'm just glad to see yours. It's good.
But I want to see yours.
It will be videotaped and
Yeah, we're
posted
recording it.
and sent to
We're not getting
all
great
FCE.
resolution.
I smell like a dog because I'm wearing wool and I got wet. Just FYI, I smell like a wet dog.
We can smell it from here.
At least I learned you can't translate between the two.
No, that's great. Actually, I think it's good that Bill led first because he kind of set the basis for carbon. And I'm one of the co-leads for the